So I am Amanda Rupiper. I am the undergraduate faculty advisor for chemical and environmental engineering. And I'm on the environmental side myself, but I advise both the chemical and the environmental, and I teach classes within the department as well. I teach the introductory class as well as a numeric methods class and the senior design and then green engineering. So I have quite a few classes, so I get to know the students pretty well and have a pretty good familiarity with both the chemical and the environmental side of things. So what I kind of want to do with this time is tell you a little bit about our department and what we do, so you can get kind of an idea of what it means to be a chemical and environmental engineer in this department. And then maybe just what it means to be a chemical and environmental engineer in general, right? If this is something you're not sure about, I can tell you a little bit more about the major, but also, what is the job opportunities and what sort of research goes on in this space and things of that nature. So I'm here. If you haven't had a chance already, I've put the department work website up as well, so you can check that out and see some pictures and see what our faculty are working on. Some really cool things happening at the website, as well as our courses and other things that I'm going to talk about in this slides as well. So, we are chemical environmental engineering. We're part of BCOE, the Bournes College of Engineering. And UCR and Bournes College have many great things going for them. We were in the top 50 public research engineering colleges in the US, number 3 Hispanic STEM graduates in the nation, number 28 for computer science, top 40 in terms of our salary potential for engineering schools, which is great. Number 6 public universities making an impact. We're very much involved, and that includes engineering, thinking about our involvement in the region, but also globally and nationally. And then we received 5 stars on our quality education, looking at things like affordability as well as outcomes, right? You're not just doing well while you're here, but you're doing well when you leave UCR as well. What does our college look like in terms of numbers? There are about 4,700, 4,800 students enrolled in engineering programs. This is across all of our engineering majors. And then 3,600 of those are specifically undergraduates, which means we have about 1,000 or a little bit more than 1,000 in our grad program, both master's and doctoral students. Why does that matter, right? Why do you care? Well, because we have a pretty robust grad program, that means that there's lots of opportunities for students to get involved in research, to pair up with a grad student, to see what's going on, to get that experience while you're still an undergrad, deciding, maybe grad school is for me, or maybe it's not. Maybe research is for me, or maybe it's not. But that chance to apply the skills you're learning in the classroom to a real world application really comes because we have that robust graduate program partnered with our undergraduate program. As a department, chemical and environmental, we make up a section of that BCOE. So about 380 students were enrolled this fall in our program. 60% or a little over 60% are declared in the chemical side of things, and about 38 or 40%-ish are enrolled in the environmental. We took on 114 incoming freshmen this year and 24 transfers. Now, the number of chemical and environmental change every year. So 60% of our department currently is chemical, but our freshman class is actually the reverse. We have 60% environmental and 40% chemical. So that number changes around, 50 plus or minus some amount. So that's the department. Those are the numbers, those are the specs. But if you're considering chemical and environmental engineering, you're probably a little bit curious, what is this major? What do you do? What sort of jobs are there? How much money are you going to make, right? These are the questions that we ask ourselves. So we're kind of a unique department because we have chemical and we have environmental combined, and we're one of the few in the US that do that. There are a handful, but only a few. But I think because they're combined, it really lends strength to each other. So chemical engineers often have to think about processes and design, and thinking about it with that environmental or sustainable perspective makes them a better chemical engineer. And our environmental engineers, as they're going out and doing things to help protect the environment, to use our resources, if they can think about the process analysis and the optimization that the chemical engineers bring to the table, they're going to do that better as well. So having these two departments together, I think, is a real strength that UCR offers. So what is a chemical engineer? I guess that's the first question. Well, chemical engineering is a branch. It's a branch of engineering that focuses on design, optimization, and management of processes that take some raw material and convert it to something that's valuable. And the most common or the traditional way we think about this is petroleum, thinking about taking crude oil and making it into gasoline or into plastic, right? Something that was raw into some final product that is marketable, right? Desirable. Other traditional routes you might think are pharmaceuticals. So people who are mass producing chemicals, that would be a traditional route as well. But chemical engineering doesn't have to be those traditional routes. In fact, chemical engineering has lots of different flavors, right? You could go into the biology piece of this, right? The biochemistry. I want to take these raw materials and I'm going to take advantage of chemical processes. But I'm also going to take advantage of biology. Maybe there's a bacteria in there that could help me produce this novel biodegradable plastic, which is one thing that chemical engineers do. Or maybe you're thinking about nanotechnology. Everything is getting smaller these days. Thinking about your smartwatch and your phone, and we've got these materials that have to go in and they have to be very, very small and precise, right? Biotechnology and biosensing, these renewable energies, these are all nanotechnologies. That also falls under this umbrella of chemical engineering. We're partnered with environmental engineering, so let's talk about that one for a second. What is environmental engineering? Well, it is engineering that focuses on design of systems, kind of like a chemical engineer. You might be thinking about a system and the process. But the environmental engineer is going to have more of a focus, right? The focus is going to be on protecting the environment, on minimizing pollution, and on managing natural resources sustainably. This could be proactive or reactive. Maybe it's reactive and you're dealing with a chemical process that produces this waste. How am I going to manage that waste stream so it doesn't harm my lakes, my rivers? How am I going to reduce the emissions so I'm not polluting the air and affecting the towns around me, right? That's kind of reactive. Maybe there's a chemical spill somewhere. An environmental engineering team might come in and be called to design the cleanup for this. How am I going to capture this spill? How am I going to process it? Maybe I'm going to pull water out. Maybe I'm going to pull soil out, or maybe I'm going to treat it right there in place. That would be an environmental engineer's job. It could also be proactive, right? It doesn't have to be, oh, we have this problem, let's deal with it. It could be, how do we prevent these problems from happening in the first place? How do we use our resources so we don't run out? How do we produce this process so it doesn't create the waste, or the waste is greener, meaning it breaks down fast in the environment, or it's not as toxic, right? That's what an environmental engineer might do. Now, that's cool, right? I'm going to go into this major and maybe I understand chemical or environmental, but the question is, of course, what am I going to do with this, right? If you're getting a degree from UCR or wherever you end up, what are you going to do when you get that degree that says chemical or environmental engineering? So let's talk about that for a second. What do chemical engineers actually do? Not what is it, but what do you actually do when you go out in the field? Well, chemical engineers are going to be designing things. They're going to be optimizing, and it really comes down to this piece, processes. How do I take something from that raw material to that final valuable product? And the real common application that you'll see from this is going to be with scale up, right? Maybe you're going to do research and we've got this novel approach to something, but it's done on a really small scale. How do I take this concept that maybe I proved at a benchtop in a lab to a full-scale manufacturing plant putting out a vaccine for millions of people when COVID comes around? How do I take this concept and I put it on this mass scale? That's what a chemical engineer does. They may see daily plant operations. They may think about safety protocols, developing new materials. Chemical engineers come up with things like polymers, pharmaceuticals, batteries, personal care products, cosmetics, refining those. So not just producing them, but how can I produce them better? How can I produce them more effectively, more efficiently, less harmfully, less environmental impact? Those are the kinds of things that a chemical engineer does in their job. Now, if you were to go look for jobs in this field, you probably wouldn't just type in chemical engineer. They hold many different titles. So if you get a degree in chemical engineering, that doesn't mean that you might be called a chemical engineer. You might be called a process engineer or an operations engineer, an R&D, a quality control specialist, product development, petroleum, nanotech, modeling and optimization specialist. So you go by many different names, which means there's lots of opportunities to take this career wherever you want, which is one of the cool things about chemical engineering. Where do they work? Well, the areas they can work are just as varied as their job titles. We often think of the big names like chemical manufacturers, pharmaceutical companies, energy companies. Think of 3M, DuPont, Union Carbide, Dow Chemical. Those are big, but chemical engineers work in smaller places as well. They can be consultants at smaller places. They can be a branch within a different facility, but you'll find them kind of all over. Now, the real question is, okay, how much money can you make, right? So that's cool, but I have to pay my bills. In 2023, the median annual salary for a chemical engineer nationally, so this is all states, not just in California, across the board, so this is my new grads and those who are later on, was 112,000 per year. Now, keep in mind that if you're in California, that number would probably be higher. And when you first start out, it might not be as high. I had some students recently, I was talking about them because they're applying for jobs right now, which is exciting, that are getting starting salaries around 80,000 to give you perspective here in California. How fast is this area growing? So the projected job growth in this field is about 8%. So over the 10 years, we expect the field to grow by 8%, which is faster than the market. So most fields grow around 4 to 5%. 8% is greater than that. So this is a growing field because there's so much demand, right? We are consumers and we make things and we want to make them better. And so to meet that demand, chemical engineers come in to do that. How about the environmentals? What do environmental engineers do? They also design and optimize processes, but those processes are going to be more on the environmental focus. So think of things like water treatment. They're going to be going out into the field if they want. So there's opportunities for field testing or going out and doing field work in the environmental side. They might design things like air pollution control systems. They might be putting together environmental impact assessments, which are done anytime you change or you build something. So there's lots of opportunities there. They might conduct site remediations. Maybe a facility came in and they left behind a bunch of contamination that now we can't use that land to build a school or a home or a neighborhood. So an environmental engineer will come in and they'll have to test the site, figure out how they can clean it up, and then return it to the public use. Think about assessing environmental risk. Right? If this pollutant is going to get out, who's at risk? How much are they at risk? Processing and analyzing data, advocacy, education, thinking about sustainability practices. The cool thing about environmental engineering is it has that technical side, but there's also that non-technical piece that you could do with these advocacy and education pieces as well. So that's what you could do. Obviously, many, many more things in there. What does the titles look like? If I'm going to go and I'm going to look for a job, what sort of jobs would I have as an environmental engineer? I could be called an environmental consultant, a water resources engineer, a sustainability coordinator, an environmental policy analyst, a remediation engineer, air pollution control engineer, conservation specialist, climate change analyst, wastewater treatment engineer, and I could go on and on, but those are some of the big ones. Where do they work? So in the chemical side, most jobs are going to be in the private sector. On the environmental side, there's going to be both private sector type jobs and public sector type jobs, which is kind of a unique piece about environmental engineering because it does have a pretty big public sector employment. Big hiring is going to be consulting firms. So you're working for these consulting firms that might get hired by a chemical manufacturer or by some facility that has a problem or has a waste or has something they're trying to make more sustainable. And they're hiring environmental engineers to come in and create that plan or to clean up their mess. As well as government agencies. So think about, the state of California. We have lots of different agencies that hire environmental engineers to make decisions, to design their own facilities to be in compliance. Utilities are a really big one, water utilities specifically, and there's the Air Resources Board for our air engineers. Research, environmental branches within manufacturing facilities. So on the private side, maybe you're going to do environmental work, but you're going to be hired directly by the manufacturer to, manage their environmental piece to be more sustainable or green or produce less waste or meet environmental regulations. How much do they make? Right, this is a perennial question. So in 2023, the median annual salary was $100,000 per year. Again, that's nationally, so in California it would probably be higher, and this is across the board, so new grads all the way to the top. Again, I just was talking with a student who just got her first job, and she was being offered $75,000 as an environmental engineer. So give you some perspective on what to expect coming out of this. Job growth in this sector is about 6%. That's pretty constant. Nice thing about environmental engineering is this is a very stable field because we're always going to need clean air. We're going to need clean water. We're going to need to clean up things so we can prevent, risk to our health and things of that nature. So this is a pretty constant thing, and part of that has to do because of these public sector jobs. So the job growth in here is about 6%, and that doesn't fluctuate a whole lot. Whereas some of our other sectors, you might find some really big job growth and then no job growth. That's not necessarily the case in this field. Okay, so that's what it means to be a chemical or an environmental engineer. This is what you could do with it. What does that look like here at UCR, right? How do I get the skills necessary to take me out to do that? So we are a department that combines them. So we have 19 faculty in our department. 11 of those are going to be on our chemical side and 8 on the environmental. So these two programs are together. We have separate classes, but a lot of the classes that our students take are together because they're learning fundamental skills that apply to both majors. On the chemical side, we have 3 different focuses. So our chemical students choose to focus in either chemical engineering, which most of our students choose, kind of the broad topic, or to focus in and go more specifically to biochemical, taking those biologic principles and applying it, and nanotechnology, thinking about things like materials and that small scale piece. Environmental engineering, we actually combined recently. So we had water and air as 2 separate, but now our students get exposure to both, but because we find that our environmental engineers really thrive when they have the ability to see how pollution and contaminants and waste moves between air and water and how they impact each other because they are not separate. And so we find that having the students have exposure to both gives them more job opportunities, but also gives them more exposure and more understanding of the topics and of the content of this major. We have these course plans. If you're interested in what sort of classes, if I'm going to be a chemical engineer, what kind of classes would I take? You can go to our website here. I have the link posted here. So you can go and you can check out the majors and you can download the course plans. This is the course plan for chemical engineers, where it lays out the different classes that a student might take by their year as well as their quarter. And you can see in the first year, students are largely taking their math, their science. And then starting in their second year, students are already getting into their major. So students might take, if you're a chemical engineer, CHE 110A, which is kind of an introduction to chemical process, thinking about that raw material process to that valuable project. And by the time students get to their 3rd and their 4th year, they're primarily taking engineering classes in their specific focus. Some of these classes, again, are going to be combined with environmentals like fluid mechanics, which everybody needs. And then they're going to have focuses that are just on chemical, like separation processes, for example. Environmental engineering also has these course plans. So if you're thinking environmental, pull up the course plan. You're going to see it's pretty similar in that students are taking the same kind of basic classes, math, science at the beginning. And then starting in their second year, they're going to start taking ENVE 171. Fundamentals of environmental engineering. And then they start getting into their major classes again in that 3rd and in that 4th year. What is so special about our department? Well, one is the classes that we take and the fact that we're combined. But the other thing that's really cool about chemical and environmental engineering at UCR is our research. We, as a department, bring in some of the largest research dollars per faculty member anybody on campus, which means that there is so much happening in our department and so many opportunities for students to get involved. If you think maybe grad school's for me, or maybe I want to see how this thing I'm learning in class directly applies, you can walk from class and walk into a research lab where you're working with maybe other peers, maybe with a grad student and another professor, and you can see it apply to the real world and get that hands-on experience while you're here. So I want to talk to you a little bit about the research going on so you can get a sense of what's happening at UCR and what sort of opportunities might exist for you if you come to join us. So we kind of break our research into these 5 categories. These are not distinct. We definitely have faculty that reach across these categories, but we kind of break them into these 5 categories where we look at advanced materials and nanotechnology, computation and molecular modeling, biotechnology and bioremediation, air quality, and water quality systems engineering. So I'm going to talk a little bit about each of these just to give you a few different key words to get a sense of what these are, so you can kind of imagine what we might be doing and what you could possibly join us in doing if you come to UCR. So when we talk about advanced materials and nanotechnology, we're thinking about design and synthesis of advanced or these nanostructured materials, right? Looking at it on this very small level, how do we structure this material? So thinking about how do these particles get assembled so we can create these materials that can go into these very small devices like sensors. It could be thinking about energy storage, thinking about how do we create batteries, or how do we use those chemical materials to then store energy. Producing nanowires, nanoparticles. It could be catalysis, thinking about single atom catalysis. How do we take advantage of catalysis to do things more efficiently, thinking about greenhouse gas reduction or utilization and other things of that nature. Lots of different things going on. And we have quite a few faculty in this area that are doing work, and all of them have taken on undergraduate students before. Biotechnology and bioremediation is when we bring in those biologic processes into the chemical engineering principles. So thinking about nanotechnology, but on this environmental biotechnology side, or metabolic engineering. Thinking about how can I take a photosynthetic organism like algae or plants to produce solutions to things that we have problems with. One example that one of our faculty is working on is he's creating plants that can photosynthesize without light. Now that sounds kind of silly, right? Photosynthesis is all about light, but he's actually managed to get a chemical-based photosynthesis process, and the application is actually going to be used for space. So he sent tomato plants up into space to look at how we can grow these plants in low light or no light environments. We've also looked at nanobiotechnology, biosensors, thinking about machine learning, biomedical engineering, so taking these small things and how do we use it for health, right? Putting things out into the world that can help on the health side of things, not just, consumption. Computation and molecular modeling, we don't have as many faculty in this. This is more the theory piece, what sort of novel chemical processes can we come up with that then can be applied to these larger manufacturing applications. If I can make this more efficient, then can I make this entire big process more efficient? So more on the theory based. Then on the environmental side, we have our water and our air faculty groups. They reach across, but mostly they focus on air and water. On the air side, we have several faculty and a pretty big research lab not far from campus where a lot of our air faculty work in these big reaction chambers, which is what you're seeing here on the slide, that big blue side. I think it's the largest reaction chamber for sure in the region. I'm not going to specifically say within what, but it's very large. And they're doing all sorts of tests on aerosol formation and smog, and thinking about the impacts of pollution from, our vehicles and our fuels, and how can we be more sustainable, and how can we be lower impact? How can we understand our impact on climate change and our impact in the atmosphere when we emit these sorts of things? On the water side, we have faculty dealing with many different things, thinking about these novel pollutants that are making it into our water. Think about all the pharmaceuticals we consume that now make it into our water, all of our personal care products that now make it into our water, and now we have to deal with it because that water doesn't just get used once, right? It comes back around. PFAS is a chemical that a lot of our faculty, or several of our faculty rather, are working on because it is so pervasive. It's just recently got regulated last year. And it's a chemical that is found everywhere. You find it in your clothes, you find it in your pots and pans. So this chemical is everywhere, and we're learning that it causes a bunch of health problems, and it doesn't break down in the environment. And so if it makes it into the water, it's going to continue in the water, and it's going to make it into your drinking water, which is a little bit problematic. So how can we think about dealing with these chemicals that are coming out that now we need to treat and figure out how we can do that effectively and efficiently and economically? We also look at other things like cleanup in the environment, microbial agents, thinking about water use efficiency, sustainability, as well as the water quality itself. Why does this matter, right? So that's all cool. I'm going into undergraduate. I'm not doing research. Well, it's because there's lots of opportunities for you to get involved. Prior to COVID, we had about 50% of our students that were involved in research in some capacity. Recently, that number is closer to 30%, but that's still a third of our students that engage in research while they are here. Maybe research is your future, maybe it's not, but even if it isn't, having the opportunity to engage in research is such a valuable thing that UCR offers because it's going to build skills, right? If you can take what you learn in a classroom and you can apply it to a lab that same day, that same week, you can talk about it with your peers, then you're going to be making these connections and you're going to be getting hands-on experience. So it's going to make you a better applicant when you go out to apply for jobs. It's going to make your resume stronger. You're going to build connections with faculty, which leads to letters of recommendation. It might lead to opportunities for grad school. It might help you when you're job seeking because you can talk about a realistic application. You can talk about how you participated in that project. So research as an undergraduate is a great opportunity. It's something that our department is really quite strong at because we do have such an active faculty base. All right, I've talked enough. I don't want to talk the whole time. I want to give some time for questions. So I'm going to open it up for questions. I know I need to check, I think, chat, or I'm not sure. I'm going to let Christina help me with the questions. But if you have questions, I would love to hear them and talk to you about it.
Yes, Dr. Rupiper, yes, we have a couple of questions. If you could put your questions in the Q&A, that would be great. The first question is, I'm interested in studying how we can use plants, fungi as a type of medicine or everyday items. Which of these types of engineering would I be interested in?
Yeah, so that's definitely a chemical engineering type aspect, and we have faculty that are doing those exact things. They're growing mushrooms, and they were doing algae growth. So that would be in our chemical engineering, in our biotechnology type field. And we have faculty, like I said, that are already doing it. So if that's something that you're interested in, I would highly encourage you to come in and maybe even meet those faculty or meet some of their grad students and talk to them about what they're doing and ask maybe if you could join one of their lab meetings or pop in and maybe get involved in that way.
This is an interesting question. Are there opportunities for collaboration between environmental and chemical engineering with fields like AI, quantum computing, or data science?
Yeah, so I love data. I teach the numeric methods, which is the data analysis class. And I can't even think of a limit to the things that you could do if you combine these skills. So our chemical and environmental, we already work really closely together. So that lots of applications or lots of collaborations there. We do have some collaborations with computer science, not as many directly, but a lot of our chemical and our environmental already apply things like machine learning and data analysis to their research because they're collecting a lot of data or they're pulling data from, public repositories or from environmental labs, and now they have to process all this data. So it's a great opportunity to build multiple skills, right? Maybe you want to build those computing skills, but you want to apply it to something that you can more directly see, like a chemical or an environmental application. And I would say lots of opportunities. We're just starting to kind of open the box on this as AI is becoming more popular. So I actually think this will grow. It's there, but I think this is a growing topic moving forward. Good question.
The next question is, what skills do you believe are most valuable for students pursuing careers in environmental or chemical engineering?
Yeah. So skills, lots of skills, hard skills and soft skills. And I think you develop both of them while you're here. Chemical and environmental engineering, both of them are based on this process idea, right? What is the process that takes this thing that I'm starting with that maybe I don't want, like a pollutant or maybe a raw material, and getting it to this form that I do want, maybe a clean environment or a desirable product. And so seeing that process piece, seeing how one piece moves to another, sometimes we call this a block flow diagram, or like this process type thinking is a generic skill that you develop the more you practice it. Other skills might be, problem solving type skills, right? If this doesn't work, what tools have I learned to approach this problem. So checking your toolbox and then trying to fit that to a problem. But then soft skills we practice are things like communication and teamwork, right? When you are working in an environmental field, you often are not working alone. When you're working in a chemical field to design a massive chemical production facility, you're not the only one working on that. So being able to communicate ideas and collaborate on ideas is a skill that's not really just chemical and environmental engineering, but it is a skill that you have to practice. And we have a senior design course where students work in a team of 5, and they get a real world problem that we partner with the community, and they solve that problem. They have 2 quarters to do that, and they build up a realistic scenario. They do the economics piece of it. They do the full scale up. They do the whole process analysis. And then at the end, they say, this is what we think you should do for all of these X, Y, and Z reasons. And they have to do it as a team. Otherwise, that problem would be way too big for a student alone to do. So I think those are some of the skills. I could keep going because there's so many different skills, but I think those are the big ones that I'll highlight for now.
Well, we have more questions.
Yes, keep going.
So, do chemical engineers work in renewable energy, like nuclear, solar, or hydropower, for example? If not, what engineers do this type of work?
They do. Not necessarily well, that's not even true. I'm gonna backtrack that. I would say yes on all of those. The hydropower, maybe not as much because there's not that chemical component. That might be an environmental engineer actually on the hydropower. Solar and nuclear, definitely because of that chemical component. And the other one that I would say that isn't included here would be things like biofuels or other renewable fuels, which very much is a chemical engineering type application. How do I take this waste product maybe and turn it into something valuable like a fuel? One example might be using algae. So algae produces this oil, and this oil is actually a really dense fuel. And if we can maximize oil production, it can be a really powerful diesel. But algae grows on wastewater, right? So we can take this thing that's not really desired, this product, to make it into something useful. Nuclear and solar are both applications. So within chemical engineering, we often have these nuclear branches. We don't focus specifically on nuclear here, but we do talk about nuclear to some degree. And then solar really comes down to the application of how you're doing it. What kind of solar are we talking about? If it's just, heat, or if we're thinking about the conversion piece and we're thinking about the chemicals involved in that conversion, that could be a chemical engineering type application. These kind of fields, renewable energies, are multidisciplinary, which makes them really exciting because that means that you're not going to be just chemical engineers working on this problem. You're probably also going to have some electrical engineers, and you're probably also going to have some mechanical engineers working on this, and maybe some civil, especially if we're thinking hydropower. So these are not they're not single focused problems, but definitely a chemical engineer could participate in all of these.
Amazing and incredible. Thank you.
Yeah.
And we have one last question. Have you ever worked on patents while pursuing your research?
Yes. So my personal research, I don't do patent type work because I'm more on the sustainability type side of it. But I was just reviewing some of our faculty's files, and they all have numerous patents, not just one patent, multiple patents. So that's definitely something that our faculty are proficient at and do on a regular basis. So if that's something that you're interested in working towards a patent, there is lots of expertise in our department to do that. I'm just not the right one for that, but I know that there's lots of people here that could help with that.
Great. Those are all the questions that we've received. So hopefully everyone who attended found this session informative, and you learned more about chemical and environmental engineering and what that looks like at UCR. And if you have any additional questions, please go to admissions.ucr.edu and pose your questions there. Anything related to admissions, applications, financial aid, etc. Thank you very much.
Like, wait, I have a slide for that. Got it.
Awesome. All right. Well, thank you so much for attending. We appreciate it.
Thank you very much.